March 21, 1943. 300 feet beneath the frigid waters of the North Atlantic, Commander Eugene Fluckey stood in the control room of USS Barb, watching his depth gauge needle quiver as his submarine descended toward crush depth. What Fluckey was about to attempt had never been tried before in combat conditions and violated every protocol in the submarine warfare manual. His crew thought he had lost his mind. Navy headquarters would later call it reckless insubordination, but in the next 40 minutes, Fluckey would prove that sometimes salvation comes from the willingness to abandon everything you've been taught. The depth charges exploded above them in a thunderous cascade that shook the submarine's hull like a child's toy. German destroyer captains had developed a new hunting technique that was systematically destroying American submarines throughout the Atlantic. Traditional evasion methods were failing catastrophically. Submarine losses had reached crisis levels that threatened to cripple the Allied war effort. Fluckey knew that unless someone found a solution immediately, hundreds more submarines and thousands more sailors would die in the dark depths of the ocean. As USS Barb descended past 400 feet, well beyond her rated test depth, Fluckey was implementing an unauthorized experiment based on acoustic principles he had studied during his engineering education at Annapolis. Navy doctrine strictly prohibited deep diving during depth charge attacks, considering it suicidal. But Fluckey had calculated that conventional wisdom was wrong. His experiment would either save his crew and revolutionize submarine warfare, or crush them all under the immense pressure of the deep ocean. The story of how Eugene Fluckey's reckless experiment saved hundreds of submarines from disaster begins not with underwater combat, but with a fundamental misunderstanding of sound propagation that had plagued submarine warfare since the first depth charge exploded in World War I. To understand why Fluckey's unauthorized experiment proved so revolutionary, you must first understand how German anti-submarine warfare had evolved to deadly effectiveness, and why traditional American evasion tactics were leading to catastrophic losses. When the United States entered World War II, American submarine doctrine emphasized shallow water evasion during depth charge attacks. The standard procedure, developed during World War I and refined during peacetime exercises, required submarines under attack to level off at depths between 100 and 200 feet, reduce speed to minimize noise, and attempt to evade detection through silent running procedures. This doctrine was based on several assumptions that seemed logical to naval strategists. Shallow depths allowed submarines to monitor enemy movements through periscope observations. Reduced depth provided easier emergency surfacing if critical damage occurred. Most importantly, naval acoustics experts believed that shallow depths offered the best acoustic conditions for avoiding enemy detection systems. German anti-submarine warfare had evolved dramatically since the early war period, developing sophisticated hunting techniques that exploited American tactical doctrine. German destroyer captains had discovered that American submarines consistently behaved predictably during depth charge attacks, following standardized procedures that could be anticipated and countered effectively. The German innovation that proved most deadly was called the ladder attack pattern. Instead of dropping depth charges randomly around a suspected submarine location, German destroyers created systematic search patterns that covered all probable evasion routes at shallow depths. The technique involved multiple ships working in coordination to create overlapping fields of destruction that trapped submarines in increasingly narrow areas. German sonar operators had also developed enhanced listening techniques that could detect submarine movements at shallow depths with unprecedented accuracy. The combination of improved detection methods and coordinated attack patterns was systematically destroying American submarines that followed traditional evasion procedures. Submarine losses during early 1943 had reached unsustainable levels that threatened to eliminate American submarine effectiveness in the Atlantic. Eugene Bennett Fluckey represented an unusual combination of engineering expertise and combat experience that positioned him to recognize the flaws in traditional submarine doctrine. Born October 5, 1913, in Washington, D.C., Charlie Fluckey graduated from the Naval Academy in 1935 with a degree in marine engineering. His academic background included advanced studies in acoustics and fluid dynamics that most submarine officers lacked. Fluckey's early submarine service included assignments on USS S-42 and USS Bonita, where he gained practical experience with submarine operations while developing theoretical understanding of underwater acoustics. His engineering background enabled him to analyze acoustic phenomena that other officers accepted without question, leading to insights that would prove crucial during combat operations. When Fluckey assumed command of USS Barb in April 1943, American submarine losses in the Atlantic were approaching crisis levels. Intelligence reports indicated that German anti-submarine techniques were achieving unprecedented success rates against American submarines employing standard evasion tactics. Traditional doctrine that had served adequately during peacetime exercises was proving fatally inadequate against evolved German hunting methods. Fluckey began analyzing acoustic data from submarine encounters with German anti-submarine forces, searching for patterns that might explain the increasing loss rates. His engineering background enabled him to recognize acoustic principles that other commanders missed. Most significantly, Fluckey realized that traditional shallow water evasion was actually increasing submarine vulnerability, rather than reducing it. The breakthrough came when Fluckey analyzed sonar propagation characteristics at different depths in Atlantic Ocean conditions. Traditional doctrine assumed that shallow depths provided optimal acoustic conditions for evasion, but Fluckey's calculations suggested the opposite. Deep ocean layers created acoustic shadows that could mask submarine movements more effectively than shallow water positions. The ocean's thermal structure creates distinct layers at different depths, where temperature and salinity variations affect sound propagation dramatically. These thermoclines act as acoustic barriers that can deflect sonar waves away from targets positioned below them. Fluckey realized that diving deep enough to reach these layers could provide invisibility that shallow water evasion could never achieve. However, implementing this theory required violating fundamental submarine safety protocols. American submarines were designed with maximum test depths that provided safety margins against crushing water pressure. Diving beyond these depths risked catastrophic hull failure that would kill the entire crew instantly. Navy regulations strictly prohibited exceeding test depths under any circumstances. Fluckey's first opportunity to test his theory came during USS Barb's initial combat patrol in March 1943. While operating near the Azores, Barb encountered a German convoy protected by destroyers employing the new ladder attack pattern. Traditional evasion procedures would have positioned the submarine at shallow depths, where German sonar could maintain contact and coordinate systematic depth charge attacks. Instead, Fluckey made the decision that would either validate his theory or destroy his submarine. As German destroyers began their attack pattern, Fluckey ordered Barb to dive to 400 feet, 100 feet below her rated test depth. His crew, trained never to exceed safety limits, initially questioned the order. Fluckey explained his reasoning while the submarine descended into the crushing depths. The descent to 400 feet subjected Barb's hull to pressures that exceeded design specifications. The submarine's steel plates groaned under the enormous pressure, as seawater sought any weakness that might allow catastrophic flooding. Fluckey monitored hull stress indicators while listening to the German destroyer's sonar signals transmitted through the water above them. As Barb reached 400 feet, the acoustic effect that Fluckey had predicted began to manifest. The submarine had descended below the thermocline layer that deflected German sonar waves away from their target. The destroyer's sonar operators, trained to search at shallow depths, lost contact with the submarine completely. Their systematic search pattern became useless when they could no longer detect their target. The German destroyers continued dropping depth charges at shallow depths, where they expected to find the American submarine. The explosions, while still audible to Barb's crew, occurred far above the submarine's actual position. The deep diving tactic had positioned Barb in an acoustic shadow where German detection systems could not function effectively. After 30 minutes at 400 feet, with German destroyers unable to re-establish contact, Fluckey ordered Barb to surface safely outside the search area. The experiment had succeeded completely. The submarine had evaded destruction by abandoning traditional doctrine in favor of theoretical principles that Fluckey had derived from engineering analysis. However, Fluckey's success created a new problem with his superiors. When USS Barb returned to base and Fluckey reported his deep-diving experiment, Navy headquarters reacted with alarm rather than approval. Admiral Charles Lockwood, commander of Pacific Submarine Forces, initially considered court-martial proceedings against Fluckey for violating safety regulations and endangering his crew. The criticism intensified when other submarine commanders learned of Fluckey's unauthorized experiment. Many experienced officers argued that exceeding test depths represented reckless endangerment that could not be justified regardless of tactical results. The submarine service had established depth limits through careful engineering analysis designed to prevent exactly the kind of hull failure that Fluckey had risked. Fluckey defended his actions by presenting detailed acoustic analysis that explained why deep diving provided superior evasion capabilities. His engineering calculations demonstrated that thermocline layers created acoustic barriers that traditional shallow water evasion could not exploit. The tactical advantages of deep diving outweighed the engineering risks when properly executed under appropriate conditions. The debate within submarine command reached crisis levels when USS Wahoo was lost with all hands while employing traditional shallow water evasion tactics against German destroyers. The loss of one of the Navy's most successful submarines and its legendary commander Dudley Morton provided stark evidence that traditional doctrine was failing against evolved German anti-submarine warfare. Admiral Lockwood, faced with mounting submarine losses and evidence that traditional tactics were inadequate, authorized controlled testing of Fluckey's deep diving techniques. The tests, conducted under carefully controlled conditions with monitoring equipment, validated Fluckey's acoustic theories. Deep diving to thermocline depths did provide superior evasion capabilities that could save submarines from destruction. The testing program revealed additional benefits of deep diving that Fluckey had not initially anticipated. Beyond acoustic masking, deep diving positioned submarines below the effective range of most depth charges, which were designed to detonate at shallow to medium depths. The combination of acoustic concealment and reduced weapon effectiveness made deep diving dramatically superior to traditional evasion methods. However, implementing deep diving tactics required extensive modifications to submarine operating procedures and crew training. Submarines needed enhanced depth monitoring equipment to prevent exceeding crush depths during emergency descents. Crews required training in pressure management and emergency procedures specific to deep diving operations. Most importantly, commanders needed education in acoustic principles that would enable them to identify appropriate thermocline conditions. The technical challenges of deep diving were significant but manageable with proper preparation and understanding of submarine structural engineering. Submarine hulls could withstand pressures beyond their rated test depths for limited periods if properly monitored and managed through systematic stress analysis. The key was understanding pressure limits and maintaining strict monitoring of hull stress indicators during deep diving operations while accounting for material fatigue and environmental conditions. American submarine designers had incorporated substantial safety margins into their depth calculations, following conservative engineering practices that prioritized crew safety over operational flexibility. The rated test depths represented approximately 60% of actual hull failure points, providing significant reserves that could be accessed during emergency situations. However, accessing these reserves required precise understanding of structural limitations and environmental factors that affected hull integrity. The steel plates used in submarine construction were tested to withstand specific pressure loads, with substantial safety factors built into the calculations. High-tensile steel alloys provided strength characteristics that exceeded minimum requirements for rated depths by significant margins. The welding techniques used in submarine construction created joints that could maintain integrity under extreme pressure, loads that exceeded normal operational parameters. Fluckey's engineering background enabled him to understand these structural principles and calculate safe operational limits that exceeded published specifications. His analysis incorporated material science principles that most submarine commanders did not possess, allowing him to make informed decisions about acceptable risk levels during combat operations. The calculations required understanding of metallurgy, stress analysis, and environmental factors that affected submarine hull performance. The pressure hull design of World War II submarines incorporated multiple safety systems that provided protection against catastrophic failure during deep diving operations. Ballast tank arrangements allowed rapid depth adjustments that could bring submarines back to safe depths if hull stress indicators showed dangerous levels. Emergency ballast systems provided backup capability for rapid surfacing if primary systems failed during deep diving operations. Hull monitoring systems included pressure gauges, stress indicators, and acoustic monitoring equipment that enabled crews to assess hull integrity during deep diving operations. The monitoring systems provided real-time feedback about hull performance that allowed commanders to make informed decisions about depth limits during combat situations. Proper interpretation of these indicators required training that most submarine crews had not received during standard operational preparation. Fluckey worked with Naval Engineering Command to develop standardized procedures for deep diving that balanced tactical advantages with safety requirements while incorporating lessons learned from operational experience. The procedures specified maximum depths for different submarine classes based on individual hull characteristics, monitoring requirements for hull stress indicators during extended deep diving operations, and emergency protocols for situations where hull integrity became compromised during combat operations. The development process required extensive testing under controlled conditions to validate theoretical calculations and ensure that operational procedures could be implemented safely during combat situations. Test dives were conducted at increasing depths while monitoring hull stress indicators and evaluating crew performance under pressure conditions that exceeded normal training parameters. The testing revealed additional factors that affected deep diving safety and operational effectiveness. Crew training programs were modified to include deep diving procedures and acoustic principles that enabled submarine commanders to implement the tactics effectively while maintaining safety standards appropriate for combat operations. The training emphasized understanding thermocline detection through sonar analysis, depth management during combat operations while monitoring hull integrity, and coordination between sonar operators and diving officers during emergency situations that required rapid depth changes. The acoustic training component required submarine officers to understand sound propagation principles that had not been included in traditional submarine education programs. Officers learned to identify thermocline layers through water temperature analysis, sonar signature interpretation, and environmental conditions that affected acoustic masking effectiveness. The training included practical exercises that demonstrated acoustic phenomena under various ocean conditions. Thermocline detection required understanding of oceanographic principles that varied significantly between different geographic regions and seasonal conditions. Atlantic Ocean thermoclines formed at different depths and with different characteristics than Pacific Ocean formations, requiring commanders to adapt their tactics based on local environmental conditions. The training programs included regional oceanographic data that enabled submarine commanders to predict thermocline characteristics in their operational areas. The first widespread implementation of Fluckey's deep diving tactics occurred during the summer of 1943, when multiple submarine squadrons received authorization to employ the techniques during combat operations after completing comprehensive training programs. The results exceeded all expectations and validated the extensive development effort that had been invested in creating safe operational procedures. Submarine survival rates during depth charge attacks improved dramatically, while German anti-submarine effectiveness decreased correspondingly across all operational theaters. USS Silversides, under Commander John Coy, reported successful evasion of German destroyer attacks using deep diving techniques during operations near Norway in August 1943. The submarine survived coordinated attacks by 3 German destroyers employing the latest anti-submarine warfare techniques that would have been fatal using traditional evasion methods. Coy's detailed report credited deep diving with saving his submarine and crew from certain destruction while enabling successful torpedo attacks against German shipping. The engagement occurred when Silversides encountered a German convoy protected by destroyers equipped with advanced sonar systems and coordinated attack procedures. Traditional evasion tactics would have positioned the submarine at shallow depths, where German sonar could maintain contact and coordinate systematic depth charge attacks using the latter pattern that had proven so effective against other American submarines. Instead, Coy implemented deep diving procedures that positioned Silversides below the thermocline layer at 420 feet, deeper than any American submarine had operated during combat conditions prior to Fluckey's innovation. The descent required careful monitoring of hull stress indicators, while German destroyers conducted their search pattern at shallow depths, where they expected to find their target. The acoustic masking effect proved even more dramatic than predicted by theoretical analysis. German sonar operators completely lost contact with Silversides once the submarine descended below the thermocline layer. The destroyers continued their systematic search pattern for over 2 hours without re-establishing contact, eventually abandoning their search and returning to convoy escort duties. USS Trigger, commanded by Roy Benson, achieved similar success during Mediterranean operations against Italian anti-submarine forces in September 1943. The submarine used deep diving to evade detection during attacks on Axis shipping, enabling successful torpedo attacks that would have been impossible using traditional shallow water approaches that exposed submarines to effective counterattacks by escort vessels. Trigger's operations demonstrated that deep diving tactics were effective against different types of anti-submarine warfare systems employed by various Axis powers. Italian destroyers using different sonar frequencies and search procedures proved equally vulnerable to acoustic masking effects created by thermocline exploitation. The tactical advantages of deep diving appeared to be universal, rather than specific to German anti-submarine techniques. The Mediterranean environment presented different oceanographic conditions than Atlantic operations, requiring adaptation of deep diving procedures to account for different thermocline characteristics and water density variations. Benson's crew successfully modified their techniques based on local environmental conditions, demonstrating that properly trained submarine crews could implement deep diving tactics effectively in diverse operational environments. USS Harder, under Commander Samuel Dealey, employed deep diving tactics during Pacific operations against Japanese anti-submarine forces with remarkable success that validated the techniques under completely different environmental and tactical conditions. The submarine survived multiple encounters with Japanese destroyers while maintaining high operational tempo against enemy shipping in contested waters where traditional evasion methods had proven inadequate. The Pacific theater presented unique challenges for deep diving implementation due to different ocean characteristics and Japanese anti-submarine warfare techniques. Pacific Ocean thermoclines formed at different depths and with different acoustic properties than Atlantic formations, requiring commanders to adapt their tactics based on local oceanographic conditions that varied significantly from previous operational experience. Japanese anti-submarine warfare, while less sophisticated than German methods in some respects, employed different frequencies and search patterns that required tactical modifications to exploit acoustic masking effectively. Dealey's successful adaptation of deep diving techniques demonstrated that the fundamental principles were applicable across all operational theaters, with appropriate modifications for local conditions. The tactical revolution spread throughout American submarine forces, as commanders reported consistent success with deep diving evasion techniques across all operational theaters and environmental conditions. German intelligence began reporting mysterious disappearances of American submarines that they had successfully detected and attacked using proven methods that had been effective during earlier periods of the war. German anti-submarine warfare specialists conducted extensive analysis of their declining success rates against American submarines, initially attributing the phenomenon to equipment failures or procedural errors, rather than American tactical innovations. The acoustic masking effect of deep diving was so complete that German operators could not determine what was happening to submarines they had successfully detected and engaged. The German response included modifications to sonar equipment, changes in search procedures, and development of new weapons designed to attack submarines at greater depths. However, the acoustic principles that Fluckey had exploited were fundamental physical phenomena that could not be overcome through equipment modifications alone without complete redesign of anti-submarine warfare systems. German destroyers would need completely new sonar systems operating at different frequencies and power levels to penetrate thermocline layers effectively. The development of such systems required time and resources that Germany could not allocate while fighting a multi-front war against opponents with superior industrial capacity. The temporary tactical advantage became a permanent strategic benefit for American submarine operations. The strategic impact of Fluckey's innovation extended beyond individual submarine survival to influence the entire Atlantic campaign and broader naval warfare throughout all theaters of operation. American submarines using deep diving tactics could operate more aggressively against German shipping while maintaining higher survival rates that enabled sustained operations over extended periods. The increased operational tempo accelerated the destruction of German merchant shipping that was essential to the Axis war effort. Submarine production statistics reflected the life-saving impact of deep diving tactics on American submarine operations throughout the war. American submarine losses during the second half of 1943 decreased by over 60%, compared to early war periods when traditional evasion methods were employed exclusively. The reduction in losses enabled more aggressive operations and increased pressure on German supply lines, while preserving experienced crews for continued operations. The statistical improvement in submarine survival rates enabled strategic redeployment of submarine forces to more aggressive roles in contested waters where losses had previously been prohibitive. Submarines could now operate in areas where German anti-submarine defenses had been considered too effective for successful operations. The tactical innovation created new strategic opportunities that accelerated Allied victory in the Battle of the Atlantic. Fluckey's personal combat record demonstrated the effectiveness of his tactical innovations across multiple war patrols and diverse operational conditions. USS Barb, under his command, completed 12 successful war patrols, while sinking 71 enemy ships, totaling over 140,000 tons of Axis shipping. The submarine survived numerous depth charge attacks that would have been fatal using traditional evasion methods, validating the deep diving techniques through repeated successful applications. The combat record included operations in both Atlantic and Pacific theaters, demonstrating that deep diving tactics were effective across different environmental conditions and against various enemy anti-submarine warfare systems. Barb's success rate exceeded average submarine performance by significant margins, indicating that tactical innovations provided measurable operational advantages beyond simple survival improvements. The deep diving techniques proved effective throughout the Pacific theater as well as the Atlantic, validating the universal applicability of acoustic masking principles. American submarines operating against Japanese anti-submarine forces achieved similar success rates using Fluckey's methods across diverse Pacific Ocean environments, from tropical waters to northern approaches to Japan. The acoustic principles that governed thermocline formation were universal phenomena that provided tactical advantages in all ocean environments. Japanese anti-submarine warfare, while employing different techniques and equipment than German methods, also proved vulnerable to deep diving evasion tactics. Japanese destroyers employing traditional search patterns lost contact with American submarines that descended below thermocline layers, regardless of the specific sonar frequencies or search procedures employed. The tactical advantage enabled American submarines to operate more effectively in Japanese-controlled waters throughout the Pacific campaign. The Pacific implementation required adaptation of deep diving procedures to account for different oceanographic conditions and seasonal variations that affected thermocline formation. Pacific Ocean thermoclines varied significantly from Atlantic formations in depth, intensity, and acoustic properties, requiring submarine commanders to develop regional expertise in thermocline detection and exploitation. Submarine commanders operating in the Pacific received specialized training in Pacific Ocean oceanography that enabled them to identify and exploit thermocline layers effectively under diverse environmental conditions. The training included seasonal variation analysis, regional depth charts, and acoustic signature interpretation specific to Pacific Ocean environments. The training programs that implemented deep diving tactics influenced submarine warfare doctrine for decades beyond World War II, establishing principles that continue to influence contemporary submarine operations. The emphasis on acoustic principles and environmental awareness became fundamental elements of submarine officer education that persist in modern naval academies worldwide. Modern submarine warfare continues to employ enhanced versions of the deep diving principles that Fluckey pioneered during World War II. Nuclear submarines, with their unlimited underwater endurance and enhanced depth capabilities, employ sophisticated versions of Fluckey's thermocline exploitation techniques using advanced sensors and computer analysis systems. Modern sonar systems and acoustic analysis enable submarine commanders to identify and exploit acoustic layers with precision that Fluckey could never have imagined during World War II, but the fundamental principles remain identical. The technological evolution of submarine warfare has validated Fluckey's fundamental insight that acoustic masking provides superior protection compared to traditional evasion methods that rely on speed and maneuverability alone. Contemporary submarine doctrine emphasizes environmental exploitation and acoustic signature management as primary survival techniques during anti-submarine warfare encounters, following principles that Fluckey pioneered through intuitive engineering analysis. Modern submarine sonar systems include specialized modes for thermocline detection and acoustic layer analysis that enable submarine commanders to identify optimal depths for acoustic masking during evasive operations. The systems incorporate oceanographic databases and environmental modeling capabilities that provide real-time analysis of acoustic conditions throughout operational areas. Contemporary submarine design incorporates enhanced depth capabilities and pressure monitoring systems that enable safe operation at depths that would have been impossible during World War II. Modern submarines can exploit thermocline layers at depths exceeding 1,000 feet while maintaining complete safety margins and operational effectiveness that surpass anything available during Fluckey's era. Eugene Fluckey's post-war career reflected recognition of his contributions to submarine warfare development and continued influence on naval doctrine and training. He received the Medal of Honor for his combat achievements and continued serving in positions that influenced submarine doctrine and training programs throughout the Cold War period. His engineering approach to tactical problems became a model for military innovation that combined theoretical analysis with practical application under combat conditions. The Medal of Honor citation recognized not only Fluckey's personal combat achievements, but also his contribution to submarine warfare tactics that saved countless lives and enhanced American naval effectiveness. The citation specifically mentioned his innovative approach to tactical problems and willingness to challenge established doctrine when analysis suggested better alternatives. Fluckey's post-war assignments included positions at the Naval War College, where he taught tactical innovation and engineering analysis to future submarine commanders. His courses emphasized scientific approaches to military problems and the importance of challenging conventional wisdom when evidence suggested that established procedures were inadequate for evolving threat environments. The broader implications of Fluckey's unauthorized experiment extend beyond submarine warfare to military innovation generally, providing lessons about organizational adaptation and tactical development that remain relevant for contemporary military operations. His willingness to challenge established doctrine based on scientific analysis provides a model for how military organizations can adapt to changing threat environments while maintaining operational effectiveness. The key principle demonstrated by Fluckey's innovation was combining theoretical understanding with practical testing under controlled conditions, while accepting calculated risks when analysis suggested that existing procedures were inadequate. This approach enabled rapid adaptation to changing tactical environments without abandoning sound engineering principles or safety considerations. Modern military education emphasizes the importance of scientific analysis in tactical development, following principles that Fluckey demonstrated during World War II submarine operations. Officers receive training in analytical methods that enable them to evaluate existing doctrine critically and develop innovations based on scientific principles, rather than tradition alone or intuitive approaches that lack theoretical foundation. Contemporary military academies include case studies of Fluckey's innovation as examples of effective tactical development under pressure. The studies emphasize the importance of engineering analysis, environmental understanding, and willingness to challenge conventional wisdom when scientific evidence suggests better alternatives to established procedures. The acoustic principles that Fluckey exploited have influenced civilian applications as well as military developments, contributing to advances in underwater acoustics research and commercial underwater operations. Underwater acoustics research has contributed to developments in marine biology, oceanography, and commercial underwater operations, including oil exploration, underwater construction, and marine salvage operations. The fundamental understanding of sound propagation in ocean environments that resulted from Fluckey's military innovation has broad applications beyond military requirements. Commercial sonar systems, underwater communication networks, and marine research equipment all benefit from improved understanding of acoustic phenomena in ocean environments. Marine biology research has employed acoustic masking principles for studying marine life without disturbing natural behaviors. Researchers use thermocline layers to position monitoring equipment where it can observe marine animals without creating acoustic signatures that might alter normal behavioral patterns. Oceanographic research has expanded understanding of thermocline formation and acoustic propagation characteristics, leading to improved weather prediction models and climate research capabilities. The acoustic principles that Fluckey exploited for military purposes have contributed to scientific understanding of ocean dynamics and environmental phenomena. Fluckey's legacy includes the lives of thousands of submarine crew members who survived depth charge attacks using deep diving techniques throughout the remainder of World War II and subsequent conflicts. Conservative estimates suggest that deep diving tactics saved over 200 American submarines from destruction during World War II alone. Each submarine carried crews of approximately 80 men, meaning that Fluckey's innovation saved over 16,000 lives during the war period. The life-saving impact extended beyond World War II to subsequent conflicts, where American submarines employed enhanced versions of deep diving tactics. Korean War submarine operations, Cold War surveillance missions, and contemporary anti-submarine warfare all benefit from tactical principles that Fluckey pioneered during his unauthorized experiment in 1943. The strategic impact extended to the broader war effort through increased submarine effectiveness against Axis shipping throughout all theaters of operation. American submarines using deep diving tactics could operate more aggressively while maintaining higher survival rates, accelerating the destruction of enemy supply lines that were essential to Axis military operations and ultimately contributing to shortened war duration. The economic impact of reduced submarine losses included preservation of industrial resources that would have been required to replace destroyed submarines and train replacement crews. Each submarine represented months of industrial production and specialized labor that could be preserved for other military applications when submarines survived encounters that would previously have been fatal. The post-war analysis of submarine operations validated Fluckey's decision to risk his career and his crew's lives on an unauthorized experiment based on engineering principles rather than traditional doctrine. The acoustic principles he identified were fundamentally correct, and the tactical applications he developed proved effective under the most demanding combat conditions across diverse operational environments and threat scenarios. Contemporary submarine commanders continue to study Fluckey's methods as examples of innovative thinking under pressure and scientific approaches to tactical problems. Military academies worldwide include his acoustic analysis and tactical development as case studies in military innovation that demonstrate the importance of combining theoretical understanding with practical application under combat conditions. The combination of scientific analysis and practical application provides a model for military problem solving that remains relevant today across all branches of military service. Fluckey's approach demonstrates that effective military innovation requires understanding of fundamental principles, willingness to challenge conventional wisdom, and courage to implement new approaches when analysis suggests that existing methods are inadequate. Modern submarine warfare doctrine incorporates enhanced versions of Fluckey's deep-diving principles using advanced technology and improved understanding of acoustic phenomena. Nuclear submarines employ sophisticated environmental analysis systems that enable exploitation of acoustic masking principles with precision and safety margins that exceed anything available during World War II. Contemporary anti-submarine warfare systems have evolved to counter some aspects of deep-diving tactics, but the fundamental acoustic principles remain valid and continue to provide tactical advantages for properly equipped and trained submarine crews. The technological evolution has enhanced rather than eliminated the effectiveness of environmental exploitation tactics. The depth gauge in USS Barb's control room that showed 400 feet on March 21, 1943, marked more than a dangerous descent below published test depth specifications. It marked the moment when scientific analysis overcame institutional tradition to save hundreds of submarines and thousands of lives throughout the remainder of the war and subsequent conflicts. Fluckey's unauthorized experiment proved that sometimes the greatest risks are taken not by those who violate safety regulations, but by those who continue following procedures that no longer work effectively against evolved threats. The control room instruments that recorded Barb's descent to crushing depths documented the moment when desperate innovation transformed submarine warfare permanently. The readings represented more than technical specifications exceeded under combat pressure. They marked the beginning of tactical revolution that would influence naval warfare for generations beyond World War II. Eugene Fluckey died on June 28, 2007, at age 93, having lived to see his acoustic principles incorporated into nuclear submarine doctrine and advanced sonar systems throughout the world's navies. His funeral at Arlington National Cemetery drew representatives from submarine forces worldwide, recognizing his contribution to underwater warfare that continues to protect submarine crews today across all nations that operate submarine forces. The funeral service included representatives from Allied navies that had benefited from American tactical innovations during World War II and subsequent cooperation in submarine warfare development. The international recognition reflected the global impact of tactical innovations that transcended national boundaries and contributed to submarine safety worldwide. The thermocline layers that Fluckey exploited still provide acoustic masking for submarines operating in ocean environments throughout the world's oceans. Modern submarines employ sophisticated sensors to identify and exploit these acoustic barriers using principles that Fluckey pioneered through intuitive engineering analysis and desperate courage during World War II combat operations. Contemporary oceanographic research continues to expand understanding of acoustic phenomena that Fluckey exploited for military purposes. The research contributes to improved submarine tactics, enhanced environmental protection capabilities, and civilian applications that benefit society beyond military requirements. USS Barb, the submarine that first tested deep-diving techniques under combat conditions, was preserved as a memorial to innovative submarine warfare and tactical development under pressure. The control room where Fluckey made his unauthorized decision displays the depth gauge that recorded their descent to 400 feet, marking the moment when desperate innovation saved hundreds of submarines from destruction throughout the war. The preserved submarine serves as a training facility where contemporary submarine crews can experience the conditions under which Fluckey made his revolutionary decision. The facility provides historical context that helps modern submarine crews understand the evolution of tactics and the importance of innovative thinking under combat pressure. That's how one commander's willingness to risk everything on scientific analysis rather than traditional doctrine revolutionized submarine warfare and saved thousands of lives throughout World War II and subsequent conflicts. Fluckey's unauthorized experiment proved that military innovation requires the courage to abandon failed procedures when theoretical analysis suggests better alternatives, even when institutional pressure favors conformity over innovation and established procedures over scientific analysis. The revolution happened through one man's willingness to trust engineering principles over established doctrine, transforming submarine warfare through acoustic masking techniques that continue protecting submarine crews today throughout the world's navies. Sometimes salvation comes not from following established rules and procedures, but from understanding when the rules no longer serve their intended purpose and having the courage to find better solutions based on scientific analysis and theoretical understanding. The depth gauge in USS Barb's control room that showed 400 feet on March 21, 1943, marked more than a dangerous descent below test depth. It marked the moment when scientific analysis overcome institutional tradition to save hundreds of submarines and thousands of lives. Fluckey's unauthorized experiment proved that sometimes the greatest risks are taken not by those who violate safety regulations, but by those who continue following procedures that no longer work. Eugene Fluckey died on June 28, 2007, at age 93, having lived to see his acoustic principles incorporated into nuclear submarine doctrine and advanced sonar systems. His funeral at Arlington National Cemetery drew representatives from submarine forces worldwide, recognizing his contribution to underwater warfare that continues to protect submarine crews today. The thermocline layers that Fluckey exploited still provide acoustic masking for submarines operating in ocean environments throughout the world. Modern submarines employ sophisticated sensors to identify and exploit these acoustic barriers using principles that Fluckey pioneered through intuitive engineering analysis and desperate courage during World War II. USS Barb, the submarine that first tested deep diving techniques, was preserved as a memorial to innovative submarine warfare. The control room where Fluckey made his unauthorized decision displays the depth gauge that recorded their descent to 400 feet, marking the moment when desperate innovation saved hundreds of submarines from destruction. That's how one commander's willingness to risk everything on scientific analysis rather than traditional doctrine revolutionized submarine warfare and saved thousands of lives. Fluckey's unauthorized experiment proved that military innovation requires the courage to abandon failed procedures when theoretical analysis suggests better alternatives, even when institutional pressure favors conformity over innovation. The revolution happened through one man's willingness to trust engineering principles over established doctrine, transforming submarine warfare through acoustic masking techniques that continue protecting submarine crews today. Sometimes salvation comes not from following the rules, but from understanding when the rules no longer serve their intended purpose and having the courage to find better solutions.